Good evening, everybody, and good evening, Ms. Pavithra Solai.
Hi, Dr. Ratan.
Yeah, I am Professor Vijay Kumar from Department of Computer Science Engineering. Students, this week we have Industry Connect. We have Pavithra Solai with us, who has more than a decade of experience. She's an entrepreneur and an AA practitioner. Her startup was the KNTKent.io, and it has been acquired by Swiggy in 2019. At Swiggy, she has been working as a data scientist, specializing in computer vision, working with interesting projects like prototyping kitchen rigs using Jetson Nano for checking food quality in restaurants, GCN-based information extraction and generating novel view synthesis for food images using 3D image painting. Pavithra enjoys building innovative models for challenging real-time problems and believes that AI's success comes from standing grounded in the reality of business problems it is designed to solve. Thank you for joining us with us, ma'am. And we look forward for an engaging and interesting session. Please take over.
Thanks, Dr. Ratan. Hi, guys. I'm Pavithra. It's the first time I'm doing a session with Jain College, and I think it's really great. Anyhow, I think people are slightly upset that RCB lost yesterday. I'm also tiny bit upset, though I'm a CSK fan myself. But then, yeah, our guys played really well. But I think let's kind of work on object detection today to maybe forget our losses in that year. So a little bit more about myself. I'm Pavithra. I'm an entrepreneur. I studied AI by myself. AI was not a big deal when I did my computer science engineering. I did it in College of Engineering, Guindy in Chennai. Don't ask when, because I'm quite old, quite ancient compared to you guys. So yeah, back then NLP to some extent was interesting, and I did a project there. And then, I worked in Microsoft and IBM, and then I started my own company. My company was called as Kint, and it is a computer vision startup that got acquired by Swiggy in 2019. I was at Swiggy till like last year, starting their computer vision projects, and we had to like create a new vertical in Swiggy itself. So it was all very interesting because we were working on India-based problems. So it was a lot of fun. I know it's in the interest of time. I thought, probably I'll get started on the presentation. So what we'll do is this. I would be, sharing the deck, and we'll be going through this. But the most important thing about any computer vision concept or any AI concept is to understand the intuition behind it, right? There's a lot of math sometimes, but then it's also about understanding why it happens so, and that is where my deck is going to be focusing on mainly. With much ado about nothing, let's get started. One second. Can you see my screen? Yeah, sorry.
Yes, madam, it is visible.
Yeah, sure. Okay, so what we are doing today is object detection 101. And in the next 15 minutes, right, let's talk about what object detection is versus what is image classification. But even before that, right, I just thought let's have a quick look at what goes on inside an CNN, right? If you have learned a little bit about convolutions, great, but let's also have a kind of intuitive look under it. And then, let's look at how are we going to solve object detection, RCNN, faster RCNN models? What is the intuition behind it? What is the intuition behind YOLO? I'm sure you have all heard about YOLO. It's you look only once. You only look once. It's not you only live once. It's only you look only once. So, and we also, if time permits, I'm just going to show like a very quick inference example, because this whole lecture, right, like object detection 101 cannot be actually put into 50 minutes. This itself is like, I don't know, like a 5-hour lecture from Andrew and G and Coursera, or probably it's a semester worth information. But it is more about being more curious about object detection, right? So first question, what is object detection, right? So you must have also heard about image classification and object detection. Let's look at these two images, right? On the left side image, you see a cat, and you're like, hey, I see a cat in the image. In the right side image, you see a cat, a dog, and a duck. Okay, but you also have to say, where is the cat, where is the dog, where is the duck? So classification is about what is in the image. Object detection is about where is that object in the image. right? So you also have to solve for where it is, like put a bounding box around it and say, hey, this is where the dog is, right? But even before that, right, I'm just going to go like a kind of a, recap on just to get an understanding of what actually happens in a convolutional network, right? Okay, so I'm going to go into experiment called as a board cat experiment. Okay, so this is in 60s and 70s. Okay, when they were doing a lot of neuroscience research, they took two cats. Okay, they took these two cats. The the one below is giving you like looking at daggers, saying, hey, I'm not going to be involved in an experiment, but this guy is looking very bored. So let's take this cat. And what they did is slightly gross. They removed the skull of the cat, and they put some electrodes inside the cat's brain, right? Okay, so you all know this mostly. This is kind of a common knowledge now that a brain consists of our brain, any other brain, right? Like it consists of neurons, right? And you have these neurons which are in kind of layers. Okay, so what they wanted to know about is, what do these neurons do when they see an image? Right. So what they did is they showed some kind of a light, like they showed like this kind of a pattern, it's straight pattern. Then they said left, right angle. They changed the different angles of it. And whenever they change the angles of it, right, certain neurons were being, activated. So if I was like, if the cat was seeing some kind of a slanted kind of a light bar, it was like, one kind of a neuron was getting activated. If it was vertical, if it was horizontal, different neurons were getting activated. So the thing that they understood is that we have neurons and we have these layers of neurons, right? And these neurons, certain neurons have certain work that they do, like wherein they get activated when they see something, right? So for example, right, if we have to find out, I'm going to draw 9, right? Like CNN doesn't know that this digit is 9. So first thing it does is it kind of breaks into two. It says, I see a circle here and I see a line coming here. If I add it together, yeah, I think it's a 9. And then they are like, okay, there's another one more circle, If I add it together, it looks like an 8. 4, I'm like, okay, one line here, another line, I'm gonna put it together, this looks like a 4, right? So essentially what actually happens here is that we're breaking down the image into smaller kind of artifacts or smaller things, like this big image, and you make it into smaller artifacts to understand what's actually making up the image, right? So in a computer vision, on a CNN, what actually happens is this. So let's say, for example, in a CNN, I have to find out that I am learning about a yellow car, right? So you would have had a look at how a CNN is, right? So I'm not going too much into the, in detail about CNNs here, but if you would know what a CNN looks like, it's basically that first you have some convolutional layers, then you have another bunch of convolutional layers, another bunch of convolutional layers, right? Let's say I'm just making a CNN. So first like 10 layers is some first convolution layer, like some 3x3 into something, and then I have some 5x5 or something of that sort. Let's say I have like layers, like bunch of layers, first batch, second batch, and third batch. So what actually happens is this: when I send an image through a CNN, right, the first few layers will understand the low level features, very low level. Okay, like for example, what is a line here, what is a circle here, that kind of a thing. Next, it will learn some kind of a slightly mid-level, then next a high-level feature. So I just want to give an example of that, right? So this is your layer 1. So lower level features of an image are like a right edge or a left edge, like what color is it, right? So those kind of things, very, very low level. Like for example, in a car, let's say a door might look like this, right? A door might look like this. So a door car, edges will be like, this is one edge, this is one edge, this is one edge, this is one edge, right? Or what is the color of the car? Like the door can be different color, maybe, it's a dual color car, etc. So those kind of features is what we take. And as we pass the output of the first layer to the next, like, first batch of layers to the next layer, right? What happens is these neurons, right? Like just like that cat thing, wherein some of these neurons were actually finding the shapes, right? So next thing it builds upon finding the shape of an image. So this is what it looks like. So let's say, for example, I'm trying to learn something like circle patterns. Can you see the green boxes? Right? When I'm trying to learn the circle patterns, right, it also kind of understands the outline of the circle pattern. So it'll be like one arc here, one arc here. I'm going to put together, okay, there is one big arc. There is another one more circle here, etc. If you look at this next one, something like, I don't know, it's something like a window or a door, right? So it's again able to find the edges there, like saying, this is what it looks like. A door comes like this, and then there is another one more edge here, right? So these are something called as like mid-level features. And some more example is like, for example, this honeycomb that you see. The next is the wheel, right? Look at the wheel and that same corresponding green box. So wheel and the spokes are being seen, right? And even with text, right, it also gets the understanding of the outline of the text. Like, for example, something is written, it's like as if you are writing it on top of another one more paper, you'll get an outline of it, right? It's something like that. The CNN is trying to understand what's in that image. If it's a text, then outline of the text. And the other one is like even the faces, like it's able to find the outline of the faces, right? Outline of the person itself. So if you see those two boxes, so one thing that I forgot to explain is the left side, what you see is actually a feature map. Okay, so when you're going to, this is a kind of a visualization. This is not how it usually happens when you're training as computer, CNN. You won't be able to get these kind of images. This is just to explain to people what's going on inside at CNN, because it's mostly like a black box. People will be like, okay, these are all numbers. I'm not able to understand what it's actually trying to represent, right? So this is kind of a representation of an image, and we call this as a feature map. You guys have to remember this. I'll ask you what a feature map is a little later in the session, right? So as and when we go a little bit, in the next layers, it's even able to find out some more advanced features. So, the thing is, one of the research found out that, about cat versus dog kind of a classification, right? How does it understand which one is a cat, which one is a dog? And these snouts, right? It's called as the nose of the dog, is called as a snout. So they use that snout to find out what type of a dog it is, what type of a cat it is, right? So these features are very, very important. So a few more that we can talk about is, so for example, eyes of the animals, right? If you look at it, the last right one. So the way it's able to understand the eye and also the features around it, right? So what do we use these features for, right? Like, yeah, I understand you're saying something like, we have neurons, and then there are layers of neurons. We just copied what's in our brain and made it into neural network. Then we're saying that the neurons will, when we learn the neural network, it learns what type of edges is it, like, with a right edge or a left edge. Using all these edges or circles and everything, we make some kind of a mid-level feature, which says like a shape kind of a thing. And then we put together, and then we say, okay, let's say, for example, there is a circle here, there is a circle here, there is a door here, there's a door here. And then there is a bonnet kind of a thing here. I'm going to put all these things together. And then I'm saying, hey, this looks like a car, right? So in a CNN, the most important thing is about learning the features of an image, right? So what are these features used for? We use it for classification, like basically saying, what's in the image, right? We look at something called as deduction, saying, what are things in the image and where is it? In the position of the image, where is it? And segmentation is one more thing, wherein we say, okay, this is the road, this is a tree, right? Wherein you can even color the image, saying, okay, these parts of the image is a tree, these parts of the road, and these parts of the image is a road, etc. So we use is something called a CV task, computer vision task, right? So this is how a kind of very simple. If you guys have worked on MNIST, it's a very simple data set, but it's like a hello world for computer vision, right? So when I'm just going to send an image, and when it goes through a neural network, right? First thing is I'm going to do all these things. First layer, I understand the edges, and then some more I find more shapes, etc. Right? In the end, right? So what we do is we make it into a vector, right? Like let's say if you wanted to show it as a logistic regression or any other classifier kind of a thing, if you have worked on it, right? So you usually send a vector, right? So we also make this input into one long vector, right? And then we send it to a classifier with a loss function and say, hey, this is the representation of the image. What do you think the image is? Is it an 8? Is it a 6? Is it a 9? And then we train the neural network to understand that it's an 8. You guys are here with me till now? This is an example of understanding that features are the most important thing in a computer in a CNN. And we're going to understand how these features are going to be used in object reduction here. Again, going back to a problem, what do we see? Classification is what is in the image. Object reduction is where is it in the image, right? And let's kind of define it as a problem statement, right? So what is the first thing? Let's say we're looking at, what are we looking at? An image in which there is a guy riding on a horse, there is a dog, there is a car, there's a person somewhere behind. So this is an output of object reduction kind of, or this is what you want the object reduction to do, right? It has to find out where the person is. It has to find out where the horse is, where the dog is, car, etc. And how do you understand? How do you say this is the position of the object, right? So you have to put a box around it. You have to put a dabba. Most of the things in computer vision is always going to be about putting a dabba around something, right? So a dabba is, this dabba is called as a bounding box, right? So how do you define the bounding box also? Like how do you draw, on a graph sheet of paper, how do you draw a square or rectangle? You will say x1, x2, y1, y2, right? So basically this will be your top left will be your x1, y2, this one will be x2, y1. So basically you have these coordinates, these numbers. Let's say I will say the box starts from 0, 0 to minus 5, 5 somewhere, right? I'm able to draw the box or draw the rectangle or a triangle, a square, etc. Right? So we are going to use these coordinates. We are going to our answer has to be like in this dabba, which is 0, 0, minus 5, 5. There is an object, and that object is a person. That is the answer for our object reduction. Right. So two things we have to, this is very, very important because in object reduction, there are two things we have to solve for. One is what is the class of the object? Where is the object? Right. I know there is an object, but what is that object? Is it a dog or a person? That is the class name. So the object, like the position of the object is given by your coordinates. Right. Okay, so now, it just so happens that, you go to college on Monday and you're like upset, RCB has lost it, but maybe GT has won or someone has won, IPL is over, and then you are like, your professor comes in and your lecturer or professor comes in and says, guys, I'm going to give you a very tough problem. Solve object reduction, right? Go and solve for it. You have to figure out ways to do it, right? So you're looking at it, one image is there. I have to find out where that option or where the position of that dog or whatever is there. How do I do it? Keep thinking. So one thing that we can do is, why don't we kind of scan the image, right? Let's take a kind of a smaller dabba, put it on the bigger dabba and keep moving it across, right? Something like this. So there is, here in this case, right, I have to find where the stingray is. I was about to say it's a whale. My biology knowledge is so bad. So, so where the stingray is. So I'm going to put this green color dabba over this bigger image, right? And I'm going to get something like a grab. I'm going to grab it and see, okay, in this segment, is there something? In this segment, is there something, etc. So for example, like the way it's going around, like just going to slow it a little bit so that you guys can see it. So if you see it, your sliding box is going like, going 1 and then 2 and 3 and 4. And you can also change the size of the sliding box also, right? So what we're going to do is we have got all these kind of screenshots. And what we're going to do next is we're going to send these screenshots are actually called as region of interest, okay? ROI, not return on investment. This is more like on the CV terms, it's ROI, the region of interest. Which region are we interested in, right? So I'm going to send that through a classifier, right? And when I send that through a classifier, what I get is, okay, I'm going to send all these dabbas, this is ROI, right? This, the right side, what you see, I'm going to send it through a classifier. And then I find that this box actually has a stingray in it. So I have found out where the stingray is and what the object, the class name is, a stingray, right? So these are things that didn't use, deep learning to some extent. This is just something like you take images, maybe convert them into vectors and send it through a SVM, and then you get this. These are a few things that happen. This was how it was done earlier, maybe in the 80s, 90s, even till 2000s. But there are issues with the sliding window algorithm, right? Let's say, for example, if you look at the right side, the video, right? Like, for example, this is the sliding box. I'm going to slide. I'm found where the car is, but the box doesn't cover the whole of the car, right? And let's say if you're going to use this in your Tesla, I'm sure you're going to go hit that car. So this method doesn't work. And if you look at the left, right? So I'm going to use a sliding box, which is mostly like what? This is horizontal, and but the person is more vertical. How do I find it? A person's object is something like this, but my box is like this. I can't get the whole person, right? So there were a lot of issues with the sliding window approach. So next thing that people did is, okay, we understand that, finding these regions of interest is more important, right? So what they did is, let's look at something called as superpixel, okay? What they're going to do is look at this image, okay? There is this girl looking at TV, right? So what they're doing in this image is that they're going to collect some of these pixels that are similar to each other, right? I'm going to color it to the same thing. Like, okay, these pixels are all black in color. This is one segment. This is one segment. So what they're going to do is they're going to keep it iteratively, keep doing it iteratively, right? So first you'll be like getting a lot of small segments, and then you make some more iterations. You will again club it together. And if you look at the last image here, right, after many iterations, you have, let's say, for example, how many regions? 1, 2, 3, 4, 5, 6, 7, 8 regions, right? So what I'm going to do is, these are called as candidate regions. And I'm going to put a dabba around it. CV, computer vision, it's all about dabbas, right? So what we're going to do is we recursively combine the smaller, similar regions into smaller ones. And we do something called as a greedy algorithm, wherein it just says, okay, this looks more like me, grab. And then you try to combine it together. And then what you have is, you have something like, after multiple iterations, a kind of a region of interest marked out, saying this region is one region, this is another one more region in an image, right? After that, what we do is we put this dabba around it, right? And then we say, okay, these dabbas look more important to us. These bounding boxes look more important to us. I'll send these bounding boxes to a SVM classifier to find out. I have to find out the person. I have to find out a TV. And then I find out, okay, I sent some 2000 boxes. In the 2000 box, one box was a TV, and another one box was a person, right? So this is how they were doing it earlier. So basically, this is the most important thing that we always have to remember. In object detection, you have to find out regions of interest in which an object could be there, right? So yeah, I understand all this, but isn't object detection like real time these days, right? Like you've seen YOLO, you've seen all these things. It's just, but how do I do all this within like a second or 2 seconds, right? I'm not going to use a GPU. Even with my laptop itself, can I do it, in real time, at least up to 2 seconds? How do I do this? This looks like a lot of process, right? So I'm just going to show you, this is a video that came almost 4 years back on YOLO V2 tiny model. Okay, so this is actually a Mission Impossible trailer that came, it's a long time came. So this actually shows, right, in real time, it's able to detect person, people, even the tie, then some action scene will come. I'm sure it's Mission Impossible. So yeah, there you go. You saw the car and the bikes. It's able to find out. Look at it's doing everything in real time actually, right? It's not following what we're doing right now, right? So just to get an example of what object detection should look like. Yeah. Awesome. Cool. Enough of Mission Impossible. Let's go back to object detection. Okay, so what do we do for object detection to work in real time? There are 2 things we also have to. Is there a question? Shall I? Sorry, how do I? You can unmute yourself and ask the question, I guess. Okay,
Anybody's having any queries?
No, I just saw someone raise their hand.
Raise the hand, yeah. It was earlier, it was done. Okay, ma'am. By the end of the session, we can address.
Okay, sure, cool. Fine. So what do we need for object detection to work in real time, right? Remember, 2 things. One is speed. Speed meaning it has to be really fast. Second thing is, even if it's fast, it should also be accurate. Otherwise, what is the point if you're going to miss a lot of important things, right? So speed and accuracy are 2 important parameters you have to keep in mind. See, all these things I've told you about, they looked at the region, then they selected the region, and then they sent it through some kind of a classifier. They got it. Okay, fine, it worked. So this is where they said, let's start using CNNs for object detection, right? And the first object detection that came up in 2015, it's called as RCNN. So it used region search the same way how we did it earlier, right? Wherein in the image, we were able to find out regions in an image and then say, okay, these are different regions, etc., right? And then it used CNNs, and then we use SVM. I know this picture is a little bit scary to look at, but be with me. So what actually happens is here, right? Earlier, if you remember, we took an image and then there are a lot of these boxes that we generated, right? Like these are all the regions of interest. Let's say, for example, an image, I can get some 2,000 or 3,000 or even 10,000 boxes. I'm going to generate saying, okay, these are all the regions of interest, right? So what they did is for each of these region of interest, so this smaller dabbas, which are smaller regions, they used a CNN on top of it, right? To get the features, and on top of it, they put a loss function to find out, bounding box regression and SVMs. I'll come to it a little bit later. So basically what they did is this. For each region of interest, they ran it through a CNN, right? So if there are 2000 regions of interest, they ran it through 2000 CNNs, right? Imagine that. So this was taking a very, very long time, though the accuracy was to some extent good. So what they did is they're thinking, why do we need to send it through 2000 CNNs, right? Let's send everything to just one CNN. That should be good enough, right? So for example, in this case, what they did is input image. Then what we do is we first get some 2000 region proposals or this ROI regions. And then for each one, we send it to a CNN, etc. And then an SVM, right? So what they did is, okay, let's make it a bit fast. It's called as a fast RCNN. So why use so many CNNs? Why can't we use one CNN? But use the feature map that you saw earlier. And from that, can we get the region of interest? Okay, I'm going to stop here. So earlier, we are getting the region of interest from the image. Now we are getting the region of interest from the feature map. So we just have to use only one convolutional network, right? Input image, you send the image, convolutional network, and then you have this kind of a feature map. And from that feature map, right, I will be using some other technique to find out what are the regions in this feature map in which I think an object is. So that's called as a region search, right? That we used one region search. You can also use different kind of algorithms. And then, we again can use a SVM or another one more kind of a regressor to find out where the position is, etc. But most important thing that you have to understand is this. In order to increase accuracy, we started to use CNNs. But instead of using 2000 CNNs, we're just going to use one CNN. But we are going to look at the ROI from the feature map, not from the image itself. And then came faster RCNN, right? So faster RCNN is, first was RCN, faster RCNN is faster RCNN. So here in this case, why are you also having a separate algorithm to find out the regions of interest? Why can't the CNN itself find this region of interest, right? So this is called as a dual stage object reduction. That is, the first stage, what you do is, you are looking at a network called as a region proposal network, in which I look at the image. And then, from that feature map, I will find out a lot of these bounding boxes saying, okay, in these regions, an object could be there, right? And these are the bounding boxes of the images. And from that, we again do another one more kind of object reduction and say, okay, in this region, which we looked at, there is a cat. In this region, we looked at, there is a dog, etc. So just to, I know this is a lot of, concepts in a little while, and I just explain it to you, but one thing is people don't understand that this is the basics that you need to understand to actually appreciate object reduction. First thing is that they said, let's slide and then find out it didn't work out. Then they said, let's look at regions. Let's just pick regions and check whether the object is there in that region. And then they said, okay, fine. Why don't we use a CNN for this, for accuracy, right? And then they also had to speed it up, saying, why use for every region of interest, one small dabba, do we use a CNN to get the feature and then do some classifier or whatever on top of it? Why don't we just put one CNN and then, get it done? Then the next thing is, even for this, why don't we do it more like a completely a CNN kind of an approach? We first do two things in this object reduction approach. First approach is region proposal, which is finding the regions of interest, wherein we are just saying in these regions, there could be an object, that's all, right? Whether it's an object or not, that's all. And then we look at those regions and say, okay, I think there is an object. Let's maybe prune that image a little bit. Okay, it has to be a little bit closer. The bounding box slightly wrong. And that, whatever is inside the bounding box is a cat or a dog or whatever class it is, right? So we have devised two stages here. One is a region proposal network. And then we're doing this. So this is what I've been talking about, right? I have only explained the model part of it. Now comes the loss function, right? Now, what are the things, again, answers we need to find? We have got our features. Yes. We have to find the position. We have to find what class the object is, right? So for position, it is a bounding box, right? And for class, it's basically saying this class is a person. Maybe if it's some other, let's say a cat or a dog, you would say in this box, it's actually a dog, right? So putting together in our AI terms, let's say, what are the things in X, Y kind of terms, right? Your X is going to be your input image. Your Y, the output is going to be the probability of the class, and BX, BY, BH, and BW, right? So basically that is nothing other than your bx comma by is your center of the box, and bw and bh are the width and the height with which you can find or draw this bounding box and say inside this bounding box C is the class car. The probability of car is maybe, I don't know, I'm just making it up 0.65 or something, right? So this is your Y. These are things that you need to find out. Okay, now is the most important thing, right? Like it's called as YOLO. I'm sure everyone has heard of it. Now they were like, the most important research that has gone through in object reduction is how can we make it faster? Even faster RCNN is not that fast. The way that, we're looking at the Mission Impossible trailer, it was so fast, right? Faster RCNN cannot do that. It can't do that in real time. Maybe now, I'm talking about then, back then couldn't do it. So there's a person who brought in a very interesting concept. He said, why do we do two, why do we need two stages? First, we have to find which region the object is and then send that region and then find out what the object is. Let's forget all that. Why can't we just do it at one shot, in a single shot, right? I have to find out what object where it is in just a single shot. I don't need to have two stages in my network. Okay. So instead of proposing regions, why can't we look at an image grid and look around it for objects? Okay, I'm going to explain this to you a little bit. Now, in a kind of a way, just forget whatever I said, right? Like we were always looking at the image, like looking at this and then saying, okay, region proposal, then this region, then everything. Instead, what I'm going to kind of challenge you is, can you get into the image? Can you, let's say, for example, there is a girl standing and then there is a cycle, right? Can you put yourself inside the image and say, okay, to my left, okay, really bad, okay, left or right? To my left, there is a cycle. To my right, there is a woman, right? Or behind me, there is a wall, etc. So you're able to understand what's happening in the image. So that's what they did. So what they did is they split the image into grids. Okay, look at this first image to the left. We split the image into 9 grids, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. You see 9 boxes? Yes. So let's say, for example, I'm going to stand in the 8th box where you see this round here, right? Like this is the box. So I'm going to stand in the 8th box. To the left and the right, if I look, I can see a car. If I look from up and down, I see a woman standing there, right? So what they introduced is, first is, make this image into kind of grids and then use something called as anchor boxes. An anchor box is nothing like, it's more like a kind of a window, right? Let's say, for example, I can only open, if I'm going to open some kind of a door or something, I'm opening like this, then I can see what is there from this side. Then I'm going to open something from here like this, from whatever I can see from here, right? So your anchor box is something like what you can see. Let's say, for example, I'm going to stand in this grid and I'm going to like kind of open up a window to the left and right, which is kind of this kind of rectangle, and see what's there. And I'm going to stand in this grid. I'm going to open a window like this up and down. I'm going to see what's there, right? So what actually they started doing is that for each grid, right, they will have like a lot of these anchor boxes, which will be like your region of interest, saying that, okay, these are all the regions that are around me. Now I have to find out whether there is an object in it and what type of an object it's there in it, right? So this is what our anchor box looks like. For each grid cell, you will have, let's say, for example, in the first YOLO, I think they had 9x9, not 9x9, 9 anchor boxes. So you can also define what type of anchor box you want. You want a more squarish, you want a very small anchor box, you want a very big anchor box. One of the things about object reduction is that, let's say, for example, you're seeing an airplane that's flying outside the window, right? It looks so small. You're going to the airport and you're seeing the airplane there. It looks so big. So scale is an issue, right? So you need to also find out smaller scaled objects and also larger scaled objects, and both can be the same class, right? So you should also have an idea about how it looks when it's small, how it looks when it's big. So what you're going to do is this: you're going to have this kind of grids in this image. You're going to have these anchor boxes, and you're going to look around the image using these anchor boxes, right? So it can be like kind of a square anchor box and say, or this kind of rectangular anchor box. So these anchor boxes, right, we are going to learn our features from these anchor boxes, and we are going to use a loss function such that for bounding box, we are going to do some kind of a regression. For which class or object it is, we are going to do something like kind of a classification. The other thing that an anchor box also helps is this, right? An anchor box can also be something like, I'm saying there is a car. You remember the car? Like I'm putting a square around the car and saying in that place there is a car, but the car is like a sedan, so it should be more vertical, right? So it should be more horizontal, right? So maybe I have to extend the bounding box of the anchor box to find, okay, this is where the car is. This is where the position of the car is. This is the segment of the car. So what they're doing is, in usual linear regression, what do? We just find the number, right? Here in this case, we just don't find the number or the coordinate. We just find the delta, like this is my box. Now, how much should this box be extended? The delta in the y direction and in the x direction, and even the center. Maybe the center has to go a little bit to this side, right? So you find the delta, you just don't find this the number. So it was even, this actually improved the accuracy even more, right? Because you don't have to worry about things like what point, small, it can be like the scale, like for example, whether it's 10, 15 or 15, 5, all these things, you don't have to do it. So this was a very interesting concept that came in and actually revolutionized object reduction. And because of this, right, like, you can do object reduction like this in real time. What took 20 minutes? And, initially when they did region search kind of thing, it took 20 minutes. Now, after they got this fast RCNN, they were able to make it in 2 minutes. And then they were able to reduce it to, let's say, 30 seconds or so, but they were not able to reduce it even further, but YOLO was able to do that, right? And this actually takes an inference of this actually takes like on a GPU, maybe 50 milliseconds, right? For just one image. What are the things that are there to look into it? But there's only one problem with YOLO. The problem is that, imagine this, okay, I'm going to have so many image grids. So usually in YOLO, when they started with the 13 cross 13 kind of, so 13 image grids. You got it, right? So, and for each grid, there's going to be 9 or 10 or 20 anchor boxes. Imagine so many boxes that are going to be there, right? But out of these boxes, only few boxes are pretty good. The other boxes are not that good information, right? They're like useless information. Have a look at the image that we have. There's so many red boxes there, which is not useful. There's no object there. I need to look at the two women, the two children, and the dog and the horse there. That is where most of the information is. So which means these anchor boxes are more important. What actually happens here is this, right? Unfortunately, what happens is, this was in YOLO V2 that they brought this in. They figured out that YOLO accuracy was suffering a lot, especially because there are a lot of these negative samples and very few positive samples. Meaning to say, there are too much of noise. There's too much of noise and we're not able to find the right signal or the right information from that noise. So what they did is this, right? They use something like, what an analogy that I call it, something called Dhoni's helicopter shot. It's called as focal loss, okay? I'm going to explain focal loss in a minute, but let me just explain, let's say, for example, you are in a cricket stadium, right? And in that cricket stadium, you are watching Dhoni. Yeah, me being a CSK fan, yeah, of course. Probably Dhoni is hitting the last, probably we need a 6 to win. And then Dhoni goes with this helicopter shot, right? And then we're all like, looking at it in awe. So you are right now not in the field, but let's say, for example, you are at home and watching this, right? Imagine this. There's so much noise around you, right? Like, for example, there will be this whole crowd that's like crowd of 50,000 shouting, saying Dhoni or CSK or RCB, whatever, right? And then you also have, let's say, the umpires telling what's actually, not umpires, sorry, the commentators actually telling what's actually happening, right? Dhoni is hitting a shot, this is kind of a ball that came in, etc. And if you're just going to hear the whole thing, what will you understand? You'll just hear everyone go, oh, I mean, it could be Dhoni is out or Dhoni hit a 6. How do you know that? So that's where a person there, right, in your Hotstar or the person there or the camera person, what they do is they will be like, let's increase the volume for the commentators and decrease the volume for the crowd, so that people who are sitting and watching it back home can understand what's actually happening. Otherwise, it's just noise. You're going to lose out the most important information, whether Dhoni is out or Dhoni hit a 6. If you're just going to listen to that noise, you won't be able to understand that. In a similar way, right, they used a different loss function in which it gave more weightage to your positive samples, the green boxes, than the red samples, right? It's just like the red samples are your crowd and this your green box commentator. So you're going to give more weightage. You're going to increase the volume, or you're going to increase the weightage for these boxes. and you're going to decrease the weightage for these boxes, the red boxes, right? So that is focal loss, right? So the thing is this, I didn't want to go even further. So this is, after this, we also have a lot more interesting neural networks that have come into picture in object reduction. And, it's basically, right, once YOLO came into picture, it was like a milestone was breached. And after that, people had to just, take YOLO cutting, and then they had to like kind of tune it for different kind of things. Like, for example, I want to find a lot of faces, like some 1,000 faces in a picture, right? Normal YOLO cannot do that. So how do you do that, right? So for that, you might have to have the different kind of a data set. You will use YOLO architecture, but you will say, hey, you know what, I'm going to tweak certain things in this architecture so that it fits the kind of data I'm going to give, and it's doing really well for faces, it's doing really well for people, etc. Or probably I can have another YOLO for just detecting cars and auto and everything else. So this is where the starting point is. And after this, right, it is more about understanding what your problem is. Let's say, for example, in Swiggy, we use something called as mask detection. Okay, like so this is something that we went live within 10 days after the COVID. I think March 26 is when we went into lockdown, right? So we wanted to check if our delivery partners were wearing the mask or not, right? So they have to check before they come to your house. We have to check whether they're wearing the mask or not. So they have to take a selfie, and in that selfie, we have to find out where the mask is, right? So the mask, the object here is a mask. So my data set will be about people wearing masks and showing where the mask is, my bounding box, and I will be, training the object detection there. Let's say, for example, for text detection, right? Like you're going on the screen on a street, and what happens is you're looking at some stop sign, right? Tesla kind of a thing, stop sign. So when you look at that, you need to find out there's a text there. So text is the object there, right? Like how face with mask was an object, your data set needs to have text. And then you do the object detection, you have text detection. So object detection is like the most core thing. Once you figure that out, you can do a lot more other stuff, right? So I know I'm running out of time. I'm just going to take a minute to show us very simple object detection example. So one thing is, I would also suggest, if you really like doing this, right? One second. Look at Andrew Ng's videos. For me, Andrew Ng is my guru. I think for like so many people out there, right? He's really great at it. So you can also have a look at it. But one thing about AI, I'm going to tell you this, right? Learn not just by yourself, learn in a group, right? Because there are a lot of things to learn, let's say in a computer vision. One person will get it, another person will get it, share your knowledge. That's how I learned, because I unfortunately didn't have a really good college like Jane College, which gave me AI course and all. I know a different kind of these kind of courses back then. Right. So let me just connect again to my Colab. What I'm showing is Colab. I'm not sure if you guys have worked on it. Colab is basically gives you a free GPU, and it's a Jupyter notebook which is hosted on a server, Google server. And I think I'm connected to a Tesla T4. So what I'm doing here is this. I'm just going to show you inferencing, because I can't show training and all these things right now, as I said. Beyond the scope of our presentation round. So here in this case, what I've done is I'm using a PyTorch version of YOLO v3, and I am installing YOLO v3 git clone from this. Ultralytics is another one more company that actually gives you YOLO v3's PyTorch version, or you can also use Darknet. Darknet, though, actually is not in TensorFlow or in PyTorch, it's in C++. So you may not have to install other dependencies, but just to make things easier. First thing is I git clone YOLO v3, then I go into the folder, then I am going to install whatever requirements I need. Then I'm going to import Torch, and from YOLO v3, I'm saying, okay, import all the utils that is needed. I'm just going to run the detect.py here, and I'm just going to look at the sample data, right? So let's say, for example, this is the sample data. Okay, so we see people, bus, and everything. Let's run YOLO v3 on top of it and see what we get, right? So this is the sample data, and I'm going to run it. So if you see here, I'm running a detect.py, which actually takes in, this is how you do it. You take you give the source image or a source video. Video doesn't run properly on YOLO, I'm sorry, on Google Colab. So I'm not going into all that. So I'm just going to run this cell, right? So this is the previous image that I had run. So it's downloading the YOLO model, 119 MB. Great, downloaded. Next, it's going to run they're going to send this image through this network. So if you see here, it took 0.4 milliseconds for pre-processing and almost 50 milliseconds for inferencing, right? Another 20 milliseconds, I'll talk about what NMS is later, but basically it's just taken maybe 70 milliseconds or so. And these are the results. It shows one person, second person. There's also one more person here. It's able to find even just the person's hand is there. It's able to find it's a person, right? You have a bus, you have another person here, right? It's actually pretty good. And there's also a cycle here. Do you see this? Even I'm going to say for the first time. Someone has a cycle on their balcony. It's able to find that cycle. Even I hadn't noticed it unless for YOLO, I would not be able to notice it. Okay, so this NMS part is a quick thing. I'll tell you, it's called as non-maximal suppression. So one is there are going to be a lot of boxes that are going to say there is an object there, right? So which box do you select? So it's basically saying which is the biggest, and so there's another one kind of an algorithm in which you will select, saying that there are a lot of boxes that show that the person is here. I'm going to use this box because the probability is good, and even the area, the cross section area is good, right? So that's called as NMS. So great. I think we've reached the end of the session. Let me just quickly also share. This is my Twitter ID, this is my LinkedIn, and I'm going to stop the sharing and let's take some questions.
Yes, students, you can just post your questions. You can just ask. Madam is available.
You can also ask me questions on computer vision. Just doesn't have to be in object reduction, right? And ask questions, guys. I'm telling you, it's more. You feel stupid and ask questions, no? The more you learn. I think that's one thing that I learned, because I learned a lot actually studying with students, because my brain cells were already dead, but students always have that curiosity.
All of them are some students, ma'am. They're having this paper.
Okay.
AML paper is there. And
okay.
They are working on all these image processing algorithms also.
Okay, got it.
I'm expecting some questions. Let us see. Hope for the best. Students, yes.
Yeah, I think everyone is like. I think any other question, just one?
Let me just check.
No issues. Reach out to me if you have any questions, guys, and all the very best for your courses.
Okay. Now questions, students? Madam is available with us. Okay, ma'am. I think it's done. We'll just wind up. And thanks a lot for your fantastic session. It was a precise briefing on the state of the art. It was very informative and guided. We are normally organize Industry Connect every Saturday. On behalf of department, I first thank resource person you, Pavithra ma'am, for being a part of the Industry Connect session. And thanks to our HOD, Dr. Vivek, and the team of faculty members for all their support. And thank you, students, for participating in this session. Take care and happy weekend.
Thank you.
Thank you. Bye.